Um, okay, so today we have a speaker from United Technologies Research Center, UTRC, Dr. Quan Long. He works in the systems department of UTRC. He has his PhD in computational mechanics from University of Cambridge, Trinity College of the University of Cambridge. He got that in 2010, and he had his master's degree from National University of Singapore and a bachelor's degree from Tianjin University in China. He was a postdoc with Institute of Computational Engineering and Sciences at University of Texas at Austin, and then also jointly at King Abdullah University of Science and Technology from 2010 to 2014. And then he became a research scientist at KAUST, King Abdullah University of Science and Technology. And then he's been in UTRC. We had an overlap in UTRC of about 2 or 3 months. And you joined UTRC last year in about a year ago? August. And I've heard he's already making significant contributions to UTRC. He's an expert in Bayesian experimental design, so that's what he's going to talk about. For just questions and answers, you can ask questions during the presentation, if that's okay with you. Sure. And that at the end also we'll try to reserve 5 or 10 minutes for questions. If you want to save them till the end, it's up to you. And then we will be here for a few, 5-10 minutes after the presentation in case you want to discuss any of the research topics or any of the presentation contents with him informally after the presentation. With that, what?
Thank you, Eva, for the invitation and the compliments. So, the topic, as you see, is efficient Bayesian optimal experimental design for physical models. My name is Quan Long, and I'm from UTRC. So, here's the outline I wanted to cover. So, there's a lot of content, so we'll do introduction, then I will tell you how to use Laplace method to accelerate the computation, also generalized Laplace method, truncated Gaussian, and multi-level Monte Carlo at the end of the talk. This is the introduction. So, experimental design is very important when resources are limited. Right? So, in the first picture, people do experiment in a laboratory. For example, this is a shock tube. They want to do the experiment and take measurements and try to infer the reaction rate of the combustion process. The second picture is about seismic inversion. The third picture is the control of HVAC system. And the third picture shows for a very large aircraft, if you want to do a health monitoring of the structural body, you probably need to know where to put the sensors. And this is also a topic of experimental design. And what is experimental design? In a very simple case, I'm showing you a linear regression model, and you want to do the regression of y on x, and you build a very simple model which is linear, and you want to know the parameter of this model, theta. And assuming that you collect all the data of y and x is the design matrix, and the simplest least square estimation of theta is theta hat, which equals x transpose times x inverse times x transpose times y. And the covariance of this estimator is sigma, which is x transpose times x inverse. So if we want the experiment to be informative, we want the covariance matrix to be as small as possible in a certain sense. So according to different optimality, we have different designs. So here's several of the alphabetic optimalities. A optimality, we want to minimize the trace of the covariance matrix. The C optimality, we want to minimize the variance of certain quantity of interest, which is a linear prediction of the theta. And d optimality, we want to minimize the determinant of the covariance matrix, which is the volume of the uncertainty. And also the a optimality. And all these are for linear models. And for nonlinear models, we would like to use the entropy-based expected information gain in a Bayesian setting. There are many computational challenges. In theory, people know everything. However, it's very difficult to compute it. The challenge comes from three parts. One is the sampler. It's very difficult to sample, to compute the utility function. Once we do that, there's another problem. It's the optimizer. And disregard all the first one and second one. Most of the time, the forward model can be very expensive to compute. But in this talk, I'm going to focus on the first subject. Here are the notation I'm going to use in the talk. Since it's in Bayesian setting, everything has a distribution. P of the P function is a probability density function, and theta is the unknown parameter we want to do inference. And theta 0 is the true parameter, which we use to generate the synthetic data. And psi is the vector of controls. And G is the deterministic model, and Y is the measurement, the data. And Y bar is a set of Yi. So we can do measurements repetitively and collect lots of data. And we assume there's additive noise in the experiment, in the observation. So you can ask me questions if you forget what are the notation stand for. In a Bayesian setting, we have a prior of the parameters, and after we collect all the data, we can use likelihood to update the prior, and it's written like this. The posterior of the theta parameter equals the likelihood times the prior and divided by a scalar. This is just to make sure everything is a density. And to measure how useful is the experiment, we can use the Kullback-Leibler divergence. It is basically a average value of the log ratio between the posterior and the prior. And you can see that if the posterior equals the prior, then the ratio equals 1 and the log is 0, and you get no information out of the experimental data. When we do the design of experiment, we don't really have the data. So we need to compute the expected information gain, which is the marginalization of the Kullback-Leibler divergence over all possible values of Y. And you can see that to compute this guy, it is very expensive because you have to sample all the possible data. And for each data, you have to do an inverse problem and compute the posterior. And if you choose to sample from the prior, which you can also do it if you rearrange the joint distribution of theta and y. And then you end up at this formula of the expected information gain. And if you do sample average, you will see that you can write the estimator of W Monte Carlo as a sample average of the log ratio. And you sample theta I from the prior, you sample yi from the likelihood. And the problem now is that you have to compute, for each sample of data, you have to compute the evidence term, which P of y. And this evidence term is another sample average. It's like you have one sample average, which is a function of another sample average. This is the so-called nested Monte Carlos. Also, it's called W Monte Carlo. If you do analysis of the estimator, you will see that the bias of this estimator is proportional to 1 over ni, which is ni is the number of samples in the inner loop, and the variance is proportional to 1 over the number of samples in the outer loop. So if you want to control the mean square error, given a tolerance to the power square, and you will end up of a total work of n naught times ni, which is to the order of tolerance minus 3. And it is well known that the Monte Carlo complexity is tolerance to the power of minus 2. And this guy is worse than Monte Carlo, and people already complain that Monte Carlo is very slow. And so how to accelerate this computation and reduce the complexity of the estimator is what I'm going to talk.
Can you please elaborate a little bit on the previous slide? How did you achieve that conclusion?
This conclusion.
Yeah.
So, if you look at, because you have to control both, right? So if you divide the total tolerance into half and control this guy and this guy, you find the relationship between the tolerance and Ni and Nl. Mm-hmm. And if you time, because the total work is a naught times Ni, right? Because it's a nested integration. And then you end up with this estimation. So Laplace method and generalized Laplace method. So the main idea of Laplace method is that asymptotically you can approximate the posterior using Gaussian distribution. Or in generalized Laplace method, you don't have you don't have Gaussian distribution, but you have a major concentration along some manifold in the parametric space. The idea of Laplace approximation is very simple. It is used to approximate such an integral, and the integrand function is an exponential function. And when m goes to infinity, you can do the truncation of f of x at x0. x0 is the global optimum of fx. And if you do this truncation and keep the second order terms, okay, this first order term is 0, right, because it's global optimum. And if you put it back, it becomes a Gaussian. Okay. And then you can do the integration directly, and the result is a function of the second derivative, of course, and also the function value of x at x naught. And of course, there's a truncation error 1 over m. So it means if you keep doing your experiments, you keep collecting lots of data, you can do this approximation, and it will be very accurate. So, of course, there's some assumption that you have a non-zero second derivative, and the third derivative is bounded because you need this truncation. And graphically, you can see that there is a concentration of measure. So we have this kind of model, and this is a very simple function. It's a posterior generated by a very simple function. And if you keep doing the measurement, you can see that the posterior start to concentrate at true value. And as long as we can do the approximation of the Gaussian distribution for the posterior, we'll see that we can carry out the part of the nested integration analytically, right? Because the posterior is a Gaussian. And then we end up with a single loop integration. So there's no double loop anymore. The first result is that the expected information gain can be computed using this integration over theta and the integration over data. And the integrand is basically the approximated Kupak-Leibler divergence in a Gaussian case. Of course, it's a function of the covariance matrix. And h here is the log of the prime. And theta hat is the map estimation. It's the maximum posterior estimation. So this is Laplace approximation. Any question? Very simple, right? Now here comes a little more challenging problem. How about this case? We have lots of parameters, but we don't have so many measurements. We cannot do too many experiments. In this case, we don't have a Gaussian posterior anymore. The first example looks like this. We have a model G. It's a scalar output. We have two parameters, theta 1 and theta 2. So in this case, it doesn't matter how many experiments you do, how many data you collect, you will never recover theta 1 and theta 2 separately, because these two, you will always recover a circle. And on this circle, you will not be able to distinguish these two parameters. And of course, there's no Gaussian estimation because there's no single point estimator anyhow. And a more physical example looks like this. If you have a cantilever beam and you have two kinds of materials, this is material 1, material 2 here, and if you put a load in the middle and you take all the measurements of the deformation, and it's not possible to recover the material elasticity, for example, of this parameter, because the parameter does not enter the equation anyhow. Now our problem is how to estimate the expected information gain. The main idea is very simple. Suppose we have a parametric domain, two-dimensional, and we have a manifold where the posterior concentrates. What we want to do is, of course, we can show that if you keep doing experiments, collecting data, the posterior will start to concentrate along this manifold. What we want to do is we found a very small region around this manifold and do a reparameterization in this region, omega m. And we define a new parameter t on the manifold and parameter s on the orthogonal direction of the manifold. And then we can guess what we can do. What we can do is basically do Laplace in the orthogonal direction, right? Because in this direction there's a single point estimation, and the conditional distribution will be a Gaussian, right? So for a fixed point on the manifold, we can do Gaussian approximation for the posterior. And here are the definitions of the machinery. The manifold is defined as a set of theta, which has this property. So the likelihood of this theta equals the likelihood of the true parameter theta naught. And we define omega m, a very small region, is a set of theta with distance to the manifold smaller than L naught times m to the power minus alpha. And we can show that this definition allows you to shrink this region. So that means when m goes to large, this omega m actually shrinks. Right? So if you're collecting more and more data, you don't need a very large omega m. And as long as alpha is between 0 and 0.5, so the rate of the shrinkage of your omega m is not faster than the posterior, then it's fine. Then you can do the approximation of Laplace, that everything will be controlled. And here are more definitions for the reparameterization. First, need to define f, which is a map between the new coordinates and the original coordinate, and also cost function, which is the quadratic form of the difference between the model theta and the true model g of theta naught. And the Hessing of f looks like this. Of course, the Hessing of f will be low rank, right? Because we have a manifold there. And therefore, u is the eigenvectors which corresponding to the non-zero eigenvalues. And if we have u, we can define the local coordinate s. S is very important because in this direction we can do Laplace approximation. Okay. And then we change the variables for the distribution of P of theta. In the new coordinate, we have P of S and T. And this is the Jacobian, the determinant of the Jacobian. And note that why I call it weight function is because they are not density anymore, because I truncated the region. Right? So the integration of this weight function is not 1 anymore. Right? Because we have Bayes' theorem, we can still have the relationship between the posterior weight function and the prior weight function. It looks exactly like Bayes' theorem. So now, come back to Kullback-Leibler divergence. The original Kullback-Leibler is an integration in the whole parametric domain, right? Since now we define two parts. The first part is omega m. The second part is everywhere else except omega m. So then we can divide the integration into two parts, and the integration outside omega m, we can show that it's exponentially small as you are collecting more and more data. And within omega m, you can change the coordinate. And you can do the integration first on the manifold t, and for fixed t, you do integration in s direction. Right? And remember that in s direction, we can do Laplace. And here is the Gaussian approximation for all the weight functions for given t and in s direction. And now we have the we can compute. We replace all the weight function using the approximated weight function, and here is Laplace error. So if we plug in everything, we end up the second result. The expected information gain becomes the integration over theta and another integration over y. This one is the indicator function, which is 1 in the omega m, which is 0 outside. And the integrand here is a function of sigma s given t. It's basically the projected covariance matrix in s direction. You just need to project it. And R is the rank of the covariance matrix. And we're not exactly very happy about this, because you still have an integration, an inner integration over the manifold, which will be potentially very expensive to compute. But fortunately, we have a very nice structure of the sigma s given t. We can decompose it into two parts. The first part is delta sigma s given t, which is independent to t for given s. The second part is dependent on t. However, it is very small if you have more and more data. And then we can plug in this approximation. We get a new formula for the expected information gain. Right? Remember that this guy is independent to t, so we can pull out this guy from the manifold integration. Right? And what's left inside is the prior. And we can really we can't really do too much about the prior, because it is the prior. And if we furthermore approximate s hat using the, it's like approximates the map estimation using the true parameter. Right? It's based on Bayesian consistency. So you will recover the true parameter. And you can remove the integration of data, and there's only one integration over the parameters. And this is the final result of the expected information gain in the underdetermined case. You can see that if you compare this formula with the previous formula, where there is a concentration of measure at a single point, it looks almost exactly the same, except that you replace the dimension of theta using the rank of the Hasse matrix. Here's R. And also you replace the covariance matrix using a projected covariance matrix. And also in that case, you have a log of the prior, but here you have a log of the integration of the prior on the underdetermined manifold. You can linearize the manifold, and approximates this prior on the manifold. And in practice, the error is very small. And now it's the truncated Gaussian approximation. Imagine that if your prior has a bounded domain. For example, in engineering, many people use uniform distribution as the prior, and in this case, you have a bounded domain. And Gaussian approximation, if the posterior of your Gaussian is spread it out, then using this Gaussian will not help you to approximate posterior, right? And graphically, you can see it like this. If you have a distribution which looks like a truncated Gaussian, but you fit this truncated Gaussian using a Gaussian by fitting the map estimation and the Hansen matrix sets the map estimation at this point. Also, locally, the shape looks exactly the same, but if you use Gaussian distribution, lots of probability mass is actually outside of your prior, and this is not good. In this case, a good thing to do it is using a truncated Gaussian. And it is very simple, this approach. And because you can compute the truncated Gaussian, compute the Gaussian, which is used to approximate the truncated Gaussian, and you do the sample from the Gaussian, and you just reject the sample outside the domain. Right? It's very fast. And the last approach I'm going to show you is the multi-level Monte Carlo for OED. The previous approach are all based on the fact that you have lots of data. Right? In some cases, you don't have too much data. If you don't have too much data, you don't have concentration of measures for the posterior. What can you do? And we can still use some method to accelerate the computation. And the method I'm going to use the multi-level Monte Carlo. And what is multi-level Monte Carlo? This slide shows the general theory. If you want to compute the estimation of a random variable, PL, actually what you want to compute is P. But PL is the approximation of the random variable on level L. For example, if you discretize some partial differential equation, you use some discretization, find an element, find a difference, find one in any method, and you can use the mesh size, for example, or the number of time discretization to control the level. Okay, and on level L, it's very expensive to compute. For example, you have lots of elements in your model. However, you can write this expectation as a telescopic sum of the difference between two consecutive levels. And the lower the level, the cheaper the model. Right? Once you build up this hierarchy, you can see that when L is very small, it's very cheap to evaluate, right? Because the model is cheap. And when the L is very big, it becomes very expensive to do the sample and compute the forward problem. However, you can see that the difference will become zero when the level becomes high, because your forward model converge. So you don't need lots of samples for the expensive models. Okay, so that's the main idea. It's a smart way to distribute your samples between expensive models and cheap models, and explore the correlation between the cheap model and the expensive model. Okay. And I'll show you the result is dramatic, and it completely changed the complexity of Monte Carlo. Okay. And the multi-level Monte Carlo estimator looks like this. You can do, of course, the first sum is over all the levels, and the second sum is basically the sample average for each level. And this is the general theorem of multi-level Monte Carlo from McGiles. Of course, the P is the random variable, and Pi is the numerical approximation of the random variable. And you can define lots of levels. And as long as you have this bounds for the weak error and strong error. Weak error is the difference between the expected difference between the random variable on level L and the true random variable, and the variance is for this random variable too. So if these guys are bounded by 2 to the power of some constant times L, and CL is the cost for each level. So for each sample on level L, the computational cost is bounded by a constant times 2 to the power of gamma times L. And gamma is, the best case of gamma is 1, because you can use the multi-grid forward solver, gamma is 1. And gamma depends on dimension too. And if you want to control the mean square error of your estimator, you can end up with this complexity. I explain a little bit more about the complexity. So the first case, when beta is bigger than gamma, that means the convergence of your variance, the decrease of your variance is faster than the increase of your cost. In this case, you have complexity of tau to the power of minus 2. This is very good in the sense that you don't see the cost of your forward model anymore. It's completely Monte Carlo, right? And in the second case, if your decrease of the variance is equals the increase of the computational cost, you have some extra term here. It's log tau. Of course, log tau is not too much. And in the third case, even if the decrease of your variance is slower than the increase of your cost, you end up with a little bit. There's the increase of complexity. But however, all these three cases are faster than the Monte Carlo, than doing Monte Carlo on the lowest level, finest level, right? How to explain this? This is Monte Carlo, right? Tau to the power of minus 2 is Monte Carlo. So you have to do all these samples. This is number of samples, tau to the power of minus 2. What is this? This comes from the cost of each sample. For one sample, you have a cost of tau to the power of minus gamma divided by alpha. This is the cost you have to pay in order to control the bias. So you can see that for all these guys, they are faster than this one. Of course, the best way is this. You don't see the cost of your simulation anymore. It's just Monte Carlo. How to use it in the experimental design? It's very nice, but I only maybe 15 minutes, and there's only slides to talk about it. You can see that for double loop Monte Carlo, we have a nested integration. It's a sample average, right, of the log ratio between the likelihood and the evidence term. And for the evidence term, you have to compute another sample average for the nested Monte Carlo. The idea here is now that we can use this sample in the inner loop to define the levels. So you don't have to use the same number of samples in the out loop and the inner loop. So it's a smart way to distribute the working load, the computational work, between the out loop and inner loop. So then you can write in a similar formula. You write the difference between PL minus 1. Right? In this case, this log is PL, and this whole thing here is PL minus 1. And the reason why I wrote it in two parts is because in this way you reduce the variance of the estimator. And we can show that the estimator has a complexity of tau to the power minus 2. It's the best you can get. However, it's probably not faster than Laplace when Laplace can be applied. This is a tool when Laplace cannot be applied. So when there's no concentration of measure, you can try this. Of course, you can also combine Laplace method and modular Monte Carlo. So in this case, if you have forward model discretized, you have finite element, for example, then you can define the levels using the mesh size, how many elements in your mesh. And then you can construct PL minus PL minus 1, and PL, of course, is the integrand in the result of Laplace approximation. And of course, here only the sigma L is defined by is dependent on the level. Because here are the applications, we don't have too much time, I'll go through it quickly and show you the main results. The first results look like this. It's a very simple example, and you can see that using Laplace approximation we can accelerate the computation by a magnitude of 1000 approximately. Remember that the blue line is double loop Monte Carlo. And these two are computed by Laplace approximation combined with sparse quadratures of Monte Carlo sampling. And in another case, I just do a change of variables, gamma equals log of theta. In this case, the manifold, you see, in the first case, the manifold is a 9, right? Because I have theta 1 plus theta 0. You see that on this straight line, 45 degrees to the horizontal line, you cannot distinguish these two parameters. In this case, I do a change of a variable, and the manifold looks like a nonlinear manifold, just to test everything. And in this case, you can see that there's basically no hope for the modular Monte Carlo. And for Laplace method, converge dramatically fast. Here's more realistic example. It's impedance tomography. We have square domain. We want to do inference on the conductivity of the bulk material. And we have 12 possible locations to put the electrodes. So every time we select two locations to put the electrodes. So from one electrode, the electricity goes in. From another electrode, the electricity goes out. So we discretize the parametric domain, the parametric space, spatially using a piecewise bilinear field. And in total, we have 16 nodal parameters. Here's basically the mesh we use to compute the forward problem. And the forward problem is Laplace equation. Here are the boundary conditions. We have zero. We have it's an integration type of boundary condition as the electrodes. We can specify the density of the electricity, and anywhere else on the boundary it is traction-free boundary condition. Also here we need to define the reference of the electric field. Right? Otherwise it will be opposed. The measurement is the integration of the potential at the selected electrodes. And the prior is the mixed Gaussian. Okay, we have two components, and we put the uncertainty around this diagonal very high. This is intentional, just to test if the results match the obvious. Okay, and the uncertainty anywhere else is very small. And here's the results. And the first two picture is the potential distribution of the two best experimental design, and the second two potential distribution is from the worst to experimental design. You can see that in the first case, most of the electricity goes through the diagonal where the uncertainty is very high. And in the second case, it's almost the same, but it's just you move these electrodes from the top side to the left side. They're very similar. But in this case, you put the electrodes on the wrong diagonal, right? And in this case, you just get very local information. You put 2 electrodes at the corner, and most of the electricity is almost zero in most of the domain. And another example is seismic source inversion. You have a square domain. You want to measure the parameters of the source of the earthquake. For example, the location of the earthquake, the magnitude of the earthquake, the starting time of the earthquake, and the frequency of the earthquake. And you take measurement on the ground. You put receivers to measure the displacement or acceleration or velocity. In this case, we just use the displacement. And of course, here's the forward model. It's basically a hyperbolic equation for linear elasticity. It's a very simple model. Here, the boundary condition, initial condition, boundary condition, traction-free boundary condition, and absorbing boundary condition, just to truncate the domain. And we take measurement y, which is the polluted displacement on the ground. And the source term has 2 parts. One is the S function, which has the frequency and the starting time. M is the momentum of the earthquake, and delta is delta function. XS is the location of the. And in total, we have 7 unknown parameters, and we have the prior for the range of the prior for these parameters. And in this case, we'll fix the total number of the receivers, and we change the distance between each of them, between 2 of them. So it's like you change the density of the receivers, but we fix the total number. And you can see that if you put all the receivers together, you don't get too much information. Right? If you sparsify these receivers, you put them too far away from each other, also the information you receive will also decrease. So there is some maximum where you get the maximum, most of the information from your data. And this distance is 1,000, and if you look at the prior, it's on the magnitude of the prior. And here's another example about shock tube experiment. And so it's basically the forward model is a set of ordinary differential equations, and you do the experiment in a shock tube, and you put the fuel and oxidizer in one end, and you put some inert gas on the other end, and if you increase the pressure, you generate the shock. Once the shock reaches the fuel and the oxidizer, the combustion happens immediately. And then we can measure the concentration of OH. It goes up very fast and then it decreases. And if we can measure the concentration, we can do the inference of the reaction constant. Also, they call it reaction rate too. And in total, there are 3 parameters. There's A parameter, B parameter, and also E parameter. And I just show you how fast is the new method. So in this case, if you directly use Laplace method, you have a huge bias. And this is the case where you have to use truncated Gaussian approximation. And you see that if you use truncated Gaussian, there's basically no bias. And I also show you, if you change the measurement error, there's some region where you can use Laplace method. But you can see that when you decrease the measurement error, that means you your posterior will start to concentrate, right? Imagine that if you have no error in your measurement, your posterior is a delta function. It's concentrated at a single point, and there's no distribution. So if you decrease this guy, within this region, you can probably directly use Laplace method, and there's no error between Laplace and the reference. But if you start to increase more and more error, the Laplace method results start to deviate from the reference. If you use truncated Gaussian method, these two stick together. And here's comparison between the convergence and the CPU. The convergence between the nested Monte Carlo and truncated Gaussian. So you can see that all these are plotted in logarithmic scale. You can see that using truncated, I should change the Laplace method to Gaussian. It's not exactly Laplace method anymore because you have to sample. You can achieve an error, acceptable error, using around 100 samples for the truncated Gaussian method compared to the nested Monte Carlo method where you need around 1 million samples. And if you compare the CPU time, you only need to run the computation for less than a second to run 100 samples for the nested Monte Carlo, but you need around 10 to the power 5 seconds to run 1 million samples for the nested Monte Carlo. So it's a huge reduction of the computation, and you get the same error, you get the same confidence. Okay? Remember that I'm not sacrificed any confidence of the results. And you can see that the truncated Gaussian method scales linearly, right? If you look at this curve, but the nested Monte Carlo scales quadratically when the sample increases. And here's more results of the combustion experiment. You see that we choose the temperature and the initial concentration of the hydrogen as two design variables. And you can see that you get the maximum information gain when you have the highest temperature and the highest hydrogen concentration, initial hydrogen concentration. And you can also see that if you increase the temperature, the information you get constantly increase. However, if you fix your temperature and you increase the initial concentration of the hydrogen, after some point, the information you get does not increase anymore. It's almost a flat curve. But at the beginning, it increased dramatically. And here I show, it's just a validation of the design results using some legacy data. And here is the result of doing two experiments. We fixed the concentration of hydrogen at the maximum value, and we choose to design two temperature in two different experiments. And we can show that if you have a big noise of your measurement, you have a maximum information gain at the highest temperature. You should do your experiment at the highest temperature in both experiments. However, if you can decrease the measurement error, the information gain you get will be different. So the best experiment, the maximum information is at the point where you have the highest temperature for one experiment and you have a almost lowest temperature in the second experiment. This is to tell you that the measurement error actually change your choice for the design. Okay, and the last slide is about the comparison of all these methods. we can see that the complexity, the worst complexity, of course, is the double loop Monte Carlo. Right? The best complexity is the multi-level Monte Carlo plus Laplace method. It's the fastest computational approach. Of course, the multi-level Monte Carlo and Laplace method plus Monte Carlo are somewhere in between. So here's the conclusion. First, we extended the Bayesian experimental design methodology based on Laplace method to the domain where we can. There's no Gaussian approximation anymore. There's only the posterior measure concentrate at some manifold. This is the so-called, we call it generalized Laplace method. And this two method has huge computational advantage over the nested Monte Carlo. And of course, when the covariance, the length of your covariance matrix is on the same magnitude of your prior, you're suggested to use truncated Gaussian in this case. And of course, if you don't have concentration of measure, and also you cannot use truncated Gaussian, we should go to multi-level Monte Carlo, which can also accelerate the computation. Here are the references of the publication. Thank you very much. Yes.
Question. So for this approach, doing the Bayesian method, the posterior and prior information and probability, does that do you have to use Gaussian distribution, or can you try other
For the prior?
for the prior?
No, you don't have to use Gaussian distribution. I have many examples which has uniform distribution.
Okay. Thank you.
This one is uniform. There are many uniform distribution. But as long as you have the Gaussianity, what I was talking about is only for the posterior.
Okay.
Yes.
Can you comment on the possibility of using these kind of approximations for dynamic state estimation? Because you don't have this information accumulation, you might not be able to obtain multiple measurements on a particular single state at a single time.
I agree. That's very interesting. But I will say common filter is basically Laplace approximation, right? Because you approximate everything is Gaussian.
Yeah.
There are many approaches to do it in a general framework. I don't. So as I said, common filter is Laplace. But if you don't have a measure of concentration, you should not use Laplace. Of course, everybody uses common filter, but common filter has a huge error when there's no Gaussianity.
Yeah.
Of course, there are some other method too. For example, some sequential Monte Carlo approach. You can directly do Monte Carlo, and using importance sampling, all this. But what I can tell you is Laplace will not work if there's no concentration of measure. But there's also some work on multi-level Monte Carlo for the dynamic state estimate.
Okay.
Yes.
Thank you.
Any other questions? I don't think we can accept the questions. Okay, so just a couple of reminders for the survey and attendance. If you have not signed in the attendance sheet, please do so, and also provide feedback. Thank you very much again, Quan. This is a small token of appreciation for your seminar. There's a little something from the UDC Institute for Advanced Systems Engineering. Thank you. Thank you to the participants for coming.